Hello and welcome to another video lesson. In this lesson, I want to talk a little bit about some algebra concepts. So the first concept I want to talk about is set theory and real numbers. What are real numbers? That's what we want to look at today. Now let's begin by defining what a set is. So we say that a set refers to the collection of objects. Collection of objects. Now, the set can be written in two notations or in two ways. The roster notation and what you call the set builder notation. So the roster and set builder notation. Those are the two ways in which you can write a set or name a set. Now, let's consider the set made up of the numbers 2, 4, 6, and 8. 2, 4, 6, and 8. Now we can write this in this roster notation or the set builder notation. So in the roster notation, this is how you write it. All right. So you have the bracket and 2, 4, 6, 8. Okay, that's the roster notation. So basically, if you think of the roster notation, you are listing. Listing. Now the set builder notation is written in this form, where we have x such that, this line means such that x is an even number between 1 and 9. So we define the same thing, 2, 4, 6, 8 in the set builder notation. All right. So we see that 2, 4, 6, 8, we can say that they're even numbers lying between 1 and 9. Okay. So let's look at two types of sets and then we'll do some practice on those sets. So I'll define the set A by 2, 4, 6, 8. Set A. Let's say A is made up of a set of numbers 2, 4, 6, and 8. And the set B, let's define that by a set of numbers made up of 2 and 6. Now we say that 4 is a member of the set A. 4 is a member of the set A. And this can be written in this form. 4 is a member of set A. So this symbol here means member of, or an element of the set. Some people can use the word belongs to. Okay, so these are different ways in this symbol can be named. So 4 is a member of set A. 4 belongs to A, the set A of 4 is an element of set A. Okay. If it does not belong to the set, then we put a line through the symbol, the slash symbol. So let's say, I can say that 4 is not an element. So I write this, it's a symbol. It's not an element of the set B. So this symbol here is not an element or not a member of the set, and so on, or does not belong to. Okay, great. Now, another symbol that I want us to define is this symbol known as a subset. Subset. Okay, subset symbol. So set B is a subset of A, since all the elements of B can be found in the set A. All right, and this is a symbol, and this is how you write it. B is a subset of A. Okay. In other words, all the elements in B, if you look here, if we come here, we see that you have two there, 6 here, 6 there, right? So these two elements, 6 and 2, you can get them out of A. That's why we say that B is a subset of A. Okay. Now there's another symbol without the line here, and this symbol, subset symbol here, is known as a proper subset. Proper subset. What does this mean? Now, it means the number of elements in set B is not equal to the number of elements in set A. So it is a proper subset, right? So proper subset. So the proper subset means that if you look at the elements here, we have B has 2 elements, right? 1, 2, this and that, 2 and 6. So 2 elements here is not equal to the number of elements in A. Okay, even though you still have 2 and 6, you can B is a subset of A, but then you have 2 elements and 4 elements here, so they are not equal. So since they are not equal, don't have the same number of elements, we say that B is a proper subset of A. Okay, so this symbol is proper subset. Proper subset. Okay. So if we count the number of elements, it's less than the elements in the other set. So it's a proper subset. So one way you can think about this symbol, think of like a less than symbol. Okay, so a less than symbol, that means number of elements here is less than the number of elements in A. Whilst for the regular subset, if it's just a subset, it could be equal to or less than, right? Equal to or less than. Okay, so let's give one example. For example, if I define another set, let's call set C, let's define that by 2, 4, 6, and 8. All right. Now, let's use the symbols here, the subset symbol. I can say that C is a subset of A. Why? Because all the elements that I have in C, 1, 2, 3, 4, 4 elements, 2, 4, 6, 8, I have the same elements. If you go to set A, you have 2, 4, 6, 8 right there. Okay, so C is a subset because all the elements can be found in A, but then it is not a proper subset because I have 4 elements in C that matches the 4 elements in A, right? So as if so you can think of that being equal number of elements. Okay, so that C is just a subset. of A. Okay, it is not a proper subset. Okay, it's not a proper subset. So we can say C is not a proper subset of A. Right. Now, one more symbol that I'll talk about, and I will look at real numbers. Now, the other symbol is the intersection symbol. Intersection. So this is the intersection symbol. Okay. Now, when we talk about intersection, we're talking about the elements common to the set under consideration, right? The element common to the set under consideration. So let's go back to our set A and set B again. So if I go back to set A, I can say that A intersection B or B intersection A. Let's say A intersection B. It means what do they have in common? So what they have in common, the set of numbers that they have in common. Here I have 2 there, 2 and 2. Let's get rid of this here. Two, 4, 6, 2 and 6. Right, so what do they have in common here? A intersection B have 2. 2 is there, 2, 2. And then you have 6 and 6. So 2 and 6 are the numbers that they have in common, right? So that's the intersection of the 2 sets. Okay, so that's the intersection symbol. So talk about like the overlap of the 2 sets. So if you think about what we call the Venn diagram, something called a Venn diagram, we're not going to go into that today, but just a quick idea of Venn diagram. If this is set A, and then let's overlap set B with that. Okay. What do they have in common? What they have in common is the intersection, the overlap here. So it means 2 and 6 will be here. Okay, common to both sets. And then what else is left in A? We have 4 and 8. So 4 and 8 will be outside the region of overlap. 4 and 8 will be here. All right. So the Venn diagram, the intersection area is where you have the overlap. The region of overlap. That's the intersection area. Okay. Okay. Now, one other symbol that I want to introduce here, and that is this union symbol. Union symbol, it's like a U, okay, means combining the sets. Okay, so if I have like A union B, it means we're putting the set together. So what would that be equal to? So we go back and compare. All right, so we have two is common to the two sets, so don't write them twice, just write it once. So you have 2, and I have 4, you have 6 and 8. So put it together, you have 2, 4, 6, and 8. The two sets put together. So if an element appears more than once, you just list it once. Okay. Right, great. So that's a quick introduction of what the set theory is about. Okay. Now I want to focus on today's lesson on real numbers. What are real numbers? Okay. So let's look at real numbers, the beginning of algebra. What are real numbers? So real numbers are the numbers all the numbers that we use in everyday life activities. Okay, they're all real numbers. Okay. So this refers to the set of all the numbers used in everyday life activity. What are the types of real numbers? There are different types of real numbers. So let's go through that. Types. So real numbers. Okay. We can break down the real numbers into what we call the rational and irrational numbers. Rational and irrational numbers. Okay. So let's begin by defining the rational numbers. Okay. So rational numbers, let's go to point D. These are numbers that can be expressed as an integer divided by a non-zero integer, right? So it's defined by the set P over Q such that P and Q are integers, but Q cannot be equal to 0. The dot cannot be equal to 0, okay? All right, so what do we mean by integers? Before we can understand this, we need to understand what integers are, right? So let's begin with the first definition, A. We have natural numbers or counting numbers, right? Natural numbers, counting numbers. So these are the numbers for counting. So it is defined by the set 1, 2, 3, 4, and 5, 6, 7, and so on. Numbers for counting. So if you can, as you can see, 0 is not a counting number. It's not a counting number. Then we have whole numbers. The whole numbers are the set of all the counting numbers or the natural numbers, including 0. So 0 is part of the whole number. So 0 is a whole number, but 0 is not a counting number, all right? So in other words, counting numbers plus 0 gives you whole numbers. Then what are the integers? The integers are the set of whole numbers, so the other whole numbers, and their opposites. Whole numbers and their opposites. So we define them by like 0, 1, 2, 3, 4, and so on, or negative numbers. So -1, -2, -4, all the way to infinity, right? Those are the integers. So whole numbers and their opposites. Okay. So now we can define the rational number very well. So integer, so P over Q are integers. That means it could be whole numbers and the opposites, P and the Q, right? Positive numbers, negative numbers, equals 0. Whole numbers and opposites. Okay. So that's the definition for rational numbers. Set defined by P over Q, such that, see the symbol, we've seen that already, such that or given that P and Q are integers. And we are saying that Q cannot be equal to 0 because we have 0 in the denominator, it's undefined, right? The number becomes defined, okay? Now, another way in which you can look at rational numbers is this. If you have a rational number and you change to the decimal, right? Decimal notation, you have what we call repeating decimals, or the decimal that terminates, right? So this is a fractional notation: 5 over 8, 12 over -7, 7 over 1, 0 over 6. These are all, rational numbers, because 5 is an integer, 8 is an integer, 12 is an integer, -7 integer, and so on. All integers, integer over integer, So that makes a rational number, okay? And in the decimal form, let's look at decimal notation. We have 5 over 8. Look at 5 over 8 here. 5 over 8, if I change to decimal, I get 0.625. 0.625. That means that this is a terminating decimal. It's a decimal that terminates, okay? This is terminates. It is a terminating decimal. So because it's a terminating decimal, it is a rational number, okay? Now let's look at the other example here. If you have 6 over 11, integer over integer, so it's a rational number. Now in the decimal form, let's see what happens. If you change the decimal, you get 0.5454. It keeps going. The dots at the end means that it's 5454 repeats. So if you look at this, you have the block of numbers repeating. This block here, 54, there's a block here, 54, repeating. So it's all right, all this can write 0.54. We were line above the 54, the block of numbers that repeats. All right, so it means 54 repeats itself. So this is a repeating decimal. Repeating. Because the repeating decimal is a rational number. Okay, one more. Look at 1 over 3. Integer, 1 is an integer, 3 over integer. So 1 over 3 it's a rational number, integer over integer. Change to decimal form, so you have 0.333, keeps going. So 3 repeats itself, so 0.3 with the line above. Okay, the same way of writing. You got the short way of writing this out. Okay, so this is a repeating decimal. So because a repeating decimal, that's also a rational number, right? So 2 ways in which you can look at rational numbers, either this or repeating or terminating decimal. Okay, rational numbers. Okay. Any other one that doesn't repeat or terminate, then we are dealing with a rational number, right? So rational numbers will be non-terminating, non-repeating decimals. Irrational numbers, sorry, irrational numbers. Irrational numbers, they will be non-terminating and non-repeating. Non-terminating and non-repeating. So it doesn't terminate and doesn't repeat. For example, if you take a number like pi, which is 22/7, right? If you divide that, you get a very long numbers, 3.14, and it keeps going. It's a very long number, no end. Okay, so pi is an irrational number. If you take square root of 2, square root of 2 is going to give a very long number, has no end, non-repeating, doesn't repeat, it doesn't terminate. So that is an example of an irrational number. Okay. If you see something like 0.6748 dots at the end like this, there's no repetition, don't see any pattern of repetition, and the dot may doesn't terminate. Because of that, it's an irrational number, and so on. All right. So those are two broad groups of real numbers. Okay. So when we come here, we can break the rational numbers down with the definitions that we have so far. We have what we call the integers, and then we can say non-integers. So under the integers, we can have the whole numbers, okay, and the negative whole numbers and negative numbers, or negative integers. In other words, the whole numbers will be the positive integers. Including 0. Okay. And then the positive integers, we can refer to them as the counting numbers. Or the natural numbers. Okay. So that's the classification of real numbers. So the next time you're given numbers, you should be able to identify them as real numbers, irrational numbers, rational numbers, integers, and so on. I think I forgot to tell you what the non-integers are. So let's add that before we end this session. So the non-integers are the fractions and decimals. Decimals. Okay. There will be the non-integers. Okay. So if you take your time to go through these short notes here, you should be able to identify the different type of numbers when given to you, right? Great. So to round up, I want to stress on the fact that if you have an integer, a rational number like this, rational number root of 3 divided by 2, right? And divided by 2, you get an irrational number. So irrational number divided by any number, you get an irrational number. So that's one point you should also take note of, right? Great. So I'll end on this point here, and then I'll see you again in my next video, where we'll be looking at algebraic expressions. Okay. See you soon. Bye-bye.